What is the number of zeros for a cubic? Well, as we discussed earlier, the fundamental theorem of algebra tells us it's a degree 3, so there'll be 3. Some may be real, some may be complex. How many critical points for a cubic? Generally, there are a maximum of n minus 1 turning points for a polynomial of degree n. So for a cubic, that means you'd see 2 actual turning points. There may be inflection points, just like we saw. This is an inflection point. It's still a critical point. It's not an actual turning point. So you want to get the terms critical, turning, and inflection points. Those are all different. So these are inflection points here, or an inflection point. These are actual turning points because the graph changes complete direction from increasing or decreasing to the opposite. And then last, what's the maximum number of real zeros? If there are 2 or 3 real zeros, they'll cross the x-axis twice, or one is a double zero, or triple zero, and there's no complex. If there are 1, then it crosses the x-axis once. The other 2 are going to be what's called complex zeros. Okay, graphs of quartic, these are degree 4, and you can start to see some patterns here. Notice the number of zeros. You're going to have 4. You're going to have 2 real zeros, and each of them are double zeros. Also notice that leading coefficient is negative, and this thing opens down, much like a parabola would if it had a negative in front of the x squared term. If we look at this second one to the right, there's 1, 2, 3, 4 real zeros. They're all different. We would expect that, and the leading coefficient was positive. Now, when you get to degree 4, you can really see some unique things. You might notice that there are some, like this is an inflection point. It's kind of strange looking. You can also look here and notice that there's going to be a complex zero because you can't get x squared to be negative. X squared will always be greater than or equal to 0. So with x squared being positive or 0 and 3 being positive, you need x to be some kind of an I, where when you square it, you get a negative 1. So that'll be something we look at as well. All right. Well, this is going to be one of your generic looking polynomials, the graph. And what's the lowest possible degree of the following function? Well, if we said that the degree minus 1 tells the turning points, we could say, if we just make some assumptions, 1, 2, 3, 4. Since there are 4 turning points, we're going to have 4 plus 1, or 5 for our degree. And based on this answer, how many zeros does it have? If we assume a degree of 5, by the fundamental theorem of algebra, we would see that there are 5 zeros. Some are real, some may be complex. In this case, 3 real zeros would exist. That's where it crosses the x-axis. And you might say, but I only see one spot and then a second spot, but this would be a double zero. And where are the critical or extreme points? Well, if we assume a degree 5, then all the critical points are the turning points. They're actually turning points, not inflection. So they would be, if I use this red marker here, they would be labeled the 1, the 2, the 3, and the 4. Those are our critical points. They're turning points. Is the degree odd or even? Leading coefficient positive or negative? Well, since the curve has n behavior that shows, and this is a notation thing, just think of x approaching negative infinity as the left-hand side, and x approaching positive infinity, you can think of that as way over on the right-hand side. So on the left-hand side, our function was down at negative infinity, and on the right side, it was up at positive infinity. So it looked something like this, where it went down to negative infinity on the left and up to positive infinity on the right. So this n behavior is something we're going to have to get into in the notation for it. The x is the horizontal position. It's going to be the left when it's at negative infinity, the right when it's at positive. And then the f of x is the y position. Is it going all the way up or all the way down? We can think of this similar to a line with a positive slope. Therefore, the leading coefficient must be a positive. We don't know what it is, but we know it must have those characteristics. Now, for a curve with an even degree, we can think of it as a parabola with squiggles in the middle. We have an odd degree, but if it was an even degree, we would notice that on the left-hand side, it approaches negative infinity, but also on the right-hand side, it approaches negative infinity, so it opens down. So the curve opens down and the leading coefficient must be negative if we had an even degree with a graph shown over here. Now let's get into this, and we're almost done with the lesson. We're going to start making some potential drawings or drawings that could be shown to have these features. Okay, let's try to make some sketches here. Draw a cubic function with a negative leading coefficient that has zeros at 1, 2, and 3. Well, 1, 2, 3, I put dots there. To be a degree 3 or a cubic, it could start down at negative infinity, come up, cross over, and look something like that. Or if the leading coefficient was negative, it could have essentially a negative sloped line that has squiggles. That would look something like this. Okay? There's an infinite amount of possible correct answers, but considering that there are two options for how this thing starts and ends, we could look at either of these. But that has to cross the x-axis at those points 1, 2, and 3. All right, draw a cubic function with a negative leading coefficient that has zeros as stated. Go ahead and try this on your own and then hit play. All right. All right, so our possible answers, there's an infinite amount of them, but we would just put a dot at negative 3 on the x-axis, negative 1 on the x-axis, and up at 4. Having a negative leading coefficient makes it look like a relative negative slope line with some squiggles, something like this. All right. Try this one. Draw a function, a cubic function with a negative leading coefficient that has zeros at negative 1, 1, and 5. Go ahead and hit pause. Okay. Something like this would work. Okay. Well, let's try drawing a quintic function with a negative leading coefficient and 3 real zeros. And what that means is I can only cross the x-axis in 3 places. And I could have some turning points in there that are some critical points that aren't obvious. This one's not an obvious degree 5, so I like to make my turning points show that it's not going to make it to the x-axis, something like this. And you see there are 1, 2, 3, 4 obvious critical points, they're turning points, but only 3 real zeros. And the fact that it's negative means it starts up at positive infinity for y and ends down at negative infinity. Now I could do, there's an infinite amount of answers. Give myself some space between the first 2 real zeros, show a squiggle in there, and then something like this. Okay, but it must start up at positive infinity on the left and end on the right at negative infinity. Why don't you try drawing a quartic function that has a double zero at 3, zeros at 1 and 5, and has a y-intercept of 0, 6. Something like this. Now what's the difference between these two graphs? One opens down, one opens up. We would know that this one has a negative leading coefficient, and this one on the right has a positive leading coefficient. We're done with the lesson. This is the on your own question. Work on this and we'll talk in class.